Hi. Hello, everyone. My name is Susana Gutarra, and today I'm going to talk to you about a research that is part of my PhD project in the University of Bristol, and that started as a master project by Alison Brimacombe and some of what are now my current supervisors. So my main focus of interest is the biomechanics and evolution of aquatic locomotion in tetrapods using fossil clades. The land-to-water transition has happened over 30 times during the evolution of tetrapods and has seen the emergence of strikingly parallel morphological adaptations. Ichthyosaurs that are the subject of this study were so well adapted to aquatic locomotion, aquatic life, that superficially resemble fish, the same as modern cetaceans. In order to understand what these transformations mean functionally, we need to go to the physics of water. And on one hand, water provides a relief from the constraints of gravity thanks to buoyancy. Thanks to buoyancy. But on the other hand, moving through water is really hard because of the thicker nature of water compared to air. So there are very large forces that resist movement, called drag, and the two main sources of this drag in fully submerged animals are the skin friction drag and the pressure drag. So these forces have to be overcome by thrust, the thrust that produces the animal, in order to move. So adaptations that maximize thrust or minimize the drag lead to an efficient locomotion. And one such adaptations that reduce drag is streamlining. So streamline shapes, which we observe in derived cetaceans and also used for engineering purposes, have the property of avoiding this wake that's produced in the back of the blunt objects. So they reduce largely the pressure component of the drag. If we want to compare the properties of drag between different shapes, we don't normally use the absolute value of the force, but instead we use, don't mind the equation, just to say that instead of force we use a non-dimensionalized coefficient, the drag coefficient, that is normalized per unit of surface area. So this number allows to say that, for example, this shape has more drag coefficient, produces more drag than this other shape. And all these forces and coefficients are very much affected by the flow regime, which is given by the simple ratio or the simple proportion or product of the velocity and the length. This is the Reynolds number. And this only says that in the realm of the large and fast animals, the forces and the flow is slightly different and proceeds more chaotically and turbulent, and the forces are completely different. This is important when we want to model flow. So is there any way to know the drag of animals? So researchers have been doing this in different ways. They have obtained forces from gliding animals, or also measure some parameters from swimming animals and use some mathematical calculations of the power and the drag, and also making models to test in water tanks. We could use this for fossils, but it's very laborious and it's expensive. So thanks to the new development or the later development of computational methods, we can do that in digital models. So computational fluid dynamics basically allows to model a flow and all the interactions of the flow with the solids in a computer. And we can do this with 2D or 3D geometry, and at the end we obtain various parameters of the flow and the forces. This only recently has been started to be used as a method to test biomechanical hypotheses in paleobiology that include external or internal flows. So we will use this to test we have used this to test the effect of the change in body plan of the ichthyosaurs during evolution, the effect of this in the drag. So ichthyosaurs have transitioned from the narrow and elongated basal forms here in yellow to modern, later to the deep body and more stocky designs of the later forms here in blue. So we have hypothesized that this change in body plan would result in a reduction of the drag coefficient through evolution. For that, to test that, we selected an array of different ichthyosauls that cover the different body shapes and all the phylogeny. And we produced full body digital reconstructions of these taxa based on different specimens of excellent preservation or published body outlines. And to this fossil taxa, we added the model of a modern analog, which is the bottlenose dolphin, for which data on drag exists experimentally. And this is what the virtual water tank experiments look like. This has been done in this software called ANSYS Fluent. To test the accuracy of these settings and the turbulence models that we use, we have validated this using standard shapes that have data on drag coefficients obtained in real water tank experiments. And we have achieved matching of these results within 5% error. So once this, the CFD is validated, we did this with all the different models. So all the models have the same length. This is, they are all scaled to 1 meter, and they have been simulated, or the flow has been simulated over different velocities, different speeds. They cover, they cover the range of Reynolds numbers in which animals of similar size move normally. They would be expected to move. And this is just a representative two-dimensional velocity plot for all these specimens. They have been modeled without and with the fins, just to test how the evolution of just the body and the contribution of the fins adds to the total drag of the total body. And these are the results of the drag coefficients for all these taxa that were analyzed. We can see in so this is again Reynolds number, so higher velocity and higher size. And we can see that they all group together, they group pretty much together in the simulations with no fins. And there's not a specific trend from the basal ones to the more modern ones. When we add the fins to the simulations, the results are a bit more scattered, and some of them increase quite substantially the drag coefficient, but still there is not any specific trends in terms of the more towards the modern. Here is just the dolphin in both of the plots, just a reference. This is just to show that the internal components of the drag, the skin friction and the pressure component and the pressure drag, are what are to be expected in a slender shape. So the majoritary component is the skin friction, so this is good. And the minor component of the pressure of the total drag is the pressure drag, and here is where most of the variability is. But still, no trend and no reduction over the evolution. So another way to compare the shapes of the different animals in terms of the drag they produce is to calculate the proportion of drag per unit of volume. And volume here we use for body mass and muscle power. So for this example here, which are two hypothetical animals of the same length swimming at the same speed, so at the same Reynolds number, we can compare the forces that are obtained by the CFD and normalize them with the value of volume that has been obtained from the 3D models. So here we can see that this Chaosaurus, in spite of producing a smaller amount of drag, has a higher proportion of drag per unit volume. And all things being equal, this means that the energetic advantage in this case would be for the dolphin, who has to generate less power to overcome the drag, because there is less drag per unit volume. So if we do this with all the different specimens, and we keep the dolphin as a basal level to which we can compare all the rest, and we call we just arbitrarily assign this 1, we can compare all the rest to it. And this is what we obtain with, and this is with different combinations of length and velocities. What we have is that only the most basal ichthyopterygians have higher proportion of drag per unit of volume compared to the dolphins, and all the rest have values that are much closer to the dolphin. We repeat all these same calculations using the fins. The trend is conserved, and it's these two that are substantially high, that have substantially higher proportion of drag per unit of volume. So these would be energetically disadvantageous for these specimens, for these body shapes. All other things being equal, of course. So to sum up, I've shown you here is that using the CFD, we've shown that there's no reduction in the drag coefficient across the evolution of ichthyosaurs, contrarily to what we had hypothesized. But nevertheless, we find that the most basal ichthyopterygians have increased proportion of drag to per unit of volume, which might have impacted in a poorer energetic performance in terms of locomotion. And we did this with a combination of 3D reconstruction techniques and CFD, which provide a robust framework to test this hypothesis in a quantitative way. And of course, having in mind all the caveats of the method, and understanding that swimming is a quite unsteady and complex phenomenon, we intend to, in the future, include some dynamic simulations to add the complexity and incorporating motion and flexibility to these models, if possible. So with this, I'd like to thank my supervisors and people from my laboratory that have helped me with software, and my funding agents, the NERDTP and the National Museum of Wales. Thank you all for listening, and do you have any questions?